Welcome to this presentation on shaft speed selection for parallel hybrids. My name is Michael and I work with Modelon, and I'm presenting this on behalf of Mälardalen University and Chalmers University, both from Sweden, as well as Romex Technology and the University of Nottingham, both from the United Kingdom. In the next 25 minutes, I will talk about the subject of this work, the methodology in terms of multi-point design and integrated modeling and simulation, and the results in terms of flow paths and mass estimates. And in the end, I will wrap up with conclusions. So here we will be discussing this parallel hybrid, which is also known as a boosted turbofan. What is this really? In essence, it's the simplest way to yield an electrified aero engine. We take a gear turbofan and bolt on an electric drive together with its power subsystem and a thermal management subsystem to dissipate all the excess heat. And you see the key components here on the schematics. The benefit is that the concept is still relatively simple in comparison to some of the other ones, and is therefore also relatively straightforward to analyze. Now, 4 variants were discussed in the literature of these parallel hybrids, and the first one here applies electric boost during the mission phases in which the aero engine must provide peak powers or peak thrust levels in relation to the cruise conditions. And these are the takeoff and to some extent also the climb conditions. And in these cases, the hybrid system draws power from batteries on board the aircraft. And therefore, it's possible to downsize the thermodynamic core to yield some of the key benefits. And this is actually the most widely concept of operations. Second, one could also apply electric boost during cruise. And some people see benefits in this, but there is also a lot of skepticism because of the weight of the required batteries. The third concept of operations shuts down the gas turbine core during taxi and spins the fan with the electric machine. The fourth and last concept installs electric machines on both the high pressure and the low pressure spool and uses these for transient control in particular to modulate the surge margin. And in the following, we will be focusing on the first option. So let's talk about the methodology then. This slide illustrates the classic single point design. And as most of you know, a single design point is used here to define the sizing of all the components. And then any number of off-design points are simulated to yield the performance estimates. Due to the limitations of the classic approach, we use multi-point design here. And in this case, design and operation rules allow off-design points also to be used to define the sizing on the design point. We therefore get this additional information flow from the right to the left. And it becomes possible to define some design choices based on key off design points. In this multi-point paradigm, we use the Kyprianides and Zhao scheme. It's fairly unchanged. And to study the shaft speed, we vary the specific thrust of the hybrid. And this is a key cycle parameter for propulsive efficiency. And a low value typically goes hand in hand with a low fan pressure ratio and a high diameter fan that reduces the losses in the wake of the engine and therefore leads to more energy efficient designs. Now, to yield consistency between the specific thrust and this fan pressure ratio, as well as the fan diameter, we augment the scheme with a correlation that you see here on the slide that was suggested by Grünstedt based on data from Grieb. And beyond this, We essentially use this Kubernetes and ZAO scheme as it was published before, with these explicit synthesis variables for the low pressure spool boost power. Additionally, we use the lens type synthesis, which applies these additional temperature ratio targets that you see on the upper right. And to modulate until we reach this target, we introduce variable low pressure spool boost power as these three synthesis variables on the bottom in the middle. And additionally, of course, we also went with Grunstedt's correlation as described on the previous slide. Here is some information on the gas turbine and aero engine modeling. To the left, you see some literature references to the underlying performance and weight estimation methodology. And to the right, you see a typical model diagram. You can see that it contains the core and the bypass flow components. There are some control blocks and a utility through which we can identify flow stations in the typical notation, and which computes some overall quantities for us. When we're building multi-point design models, these models, as we just saw them, can be instantiated several times. Typically, that happens once for design and several times for off design. And these engine model instances are then connected to each other through additional utility models that contain the typical design and operation rules. Thanks to the standardized Modelica modeling language, all the graphical and textual representations of the model are always consistent. And we can also open up the code editor in the environment to read and change the code by hand anytime. Now, if we want to yield an integrated simulation in design, we also must include some physical models of the electric power system. And these can be introduced through these placeholders. Behind that, we can have different variants. And by replacing the placeholder with a particular variant, we drop in just the right model detail. In this case, the electric machine, the cables, the inverter, batteries, and so on. Lastly, we can also review some of the geometric dimensions used in the analytic design procedure for the electric machine. And as you can see here, we assume a permanent magnet synchronous machine design and a certain constant cooling flow in terms of oil, 5 kilograms per second across all the cases, across all the designs that we're looking at. And the references on the slide, they provide some more detail on this analytic sizing procedure that I mentioned. All the computations were run in ModelOnImpact, the system simulation platform that offers multiple views and means to access modeling and simulation. And on the slide to the left, you see the graphical desktop with your drag and drop functionality and these custom functions or microscripts that can be used to automate workflows interactively. In the middle, you see the notebook interface in which you can mix code, text, graphics, outputs, plots, etc., to build up sophisticated analyses and workflows. And to the right, you see your casual web apps and browser-based dashboards providing interfaces to sophisticated simulation. And in this work, we use the two views shown to the left. Now, these views, they allowed us to create a customizable workflow covering this drag and drop interface to build the normal single point plant model. That also allows us to save and name single point simulation results, and which also can be used to automatically generate a stub for the multi-point model from which we expand and graphically create the complete multi-point setup. And that also gives us support to reuse the saved and named single point simulation results to initialize the model the first time you run it. And lastly, we use the interactively built and converged multi-point model in these analysis notebooks. Here is an example of step 3, where we converge the multi-point model. We reuse these tagged single point results as guesses, and we have to define a mapping between the names of the results and the names of the submodel instances, as you see here on the screen. And then we switch off saving the results into another initialized model as a separate experiment and run the multi-point simulation, and of course come up with a meaningful name such as the OPER 50 that you see here. An example of the step 4 with an analysis notebook. Here we use the same server-based on-premise server-based infrastructure and run a workflow with batch analyses where we dump results into a slideshow presentation. So you will see the plots popping up first in the notebook and then in your slideshow file. So let's move on to the results. Here are some typical cycle performance results. Here we're using color coding for the different cases. And when we have roughly the same case, independently of how we call it in a given scheme, we color it with the same color. So for instance, your orange is rolling takeoff and max takeoff. And the line style refers to the different multi-point schemes. So for instance, you got your dotted lines for table 1, which is the Kyprianides and Zhao multi-point scheme, and your solid lines for table 2, which was the lens type synthesis. And what are we really getting? So first, for the conventional and hybrid Cranfield type designs, we get this expected specific fuel consumption improvement. We also see that bypass ratio increases mildly. And for the conventional and hybrid NASA Glenn type designs, so including the lens type scheme, we also get some expected specific fuel consumption improvements. The bypass ratio here also reduces quite a bit, but it's also already on a very high level. By design, the overall pressure ratio is not changing. That was contained in how we built the multi-point synthesis schemes. Now here we see that all the Glenn type designs, so for the conventional and the hybrid designs, they actually create very high bypass ratio designs with low turbine inlet temperature. Now the Cranfield designs in turn, they generate much more compact designs, so lower fan diameter and lower bypass ratio. So therefore they have better drag and weight. Additionally, and you can see some more information on that in the paper, the Glenn type designs, they also have a rather high cruise thrust, which then also leads to worse specific fuel consumption when we're throttling down to even lower turbine inlet temperatures to get just the right thrust. And for these reasons, in the following, we will only cover the Cranfield type scheme. So Cranfield for the conventional designs and Kyprianides and Zhao for the hybrid electric ones. And you can find more details on the Glenn type designs, including the lens type for the hybrid electric in the paper. Now I want to emphasize one additional fact. Despite this fully coupled design and simulation, these cycle results, they're actually made independent of the electric machine installation option, the machine sizing, and the physical dimensions of the gas turbine. And in the following, we will be showing you some cut views or flow paths together with the machine installation options. And these then vary from one option to another. So here you see different machine installation options. if we start from the left, we see how the machine could be installed inside the intermediate pressure compressor. And then we actually assume that it can only be connected to the low pressure turbine side of the fan gearbox. Alternatively, and you can see this in the middle and on the right, it could be installed inside the spinner. And there we assume that it could be connected either to the low pressure side, low pressure turbine side, or the fan side of the fan gearbox. And yeah, that's what you see in the middle and to the right, respectively. Now, if we review the different flow paths for different values of the specific thrust, we see that as we go to lower values of the specific thrust, the speed is reduced while we maintain essentially constant power. So we have to generate more torque, and the machine lengths, they increase quite a bit. At the bottom, we see machine efficiency and rolling takeoff. Now here the legend corresponds to the flow paths that you see to the top from right to left. So your spinner at fan installation shown to the right uses your dotted line. The spinner at the low pressure turbine in the middle uses the solid line, and the intermediate pressure compressor at the low pressure turbine shown on the left uses your dashed line. And we can see here that the impact of mounting to a different side of the gearbox is fairly small. You have to take into account that we have a gear ratio of roughly 3, but on the efficiency, there isn't much difference. As we go to lower specific thrust, we see that the hub diameters become larger, and there is also this particular efficiency trend, which we can explain if we recall that the copper losses are increasing with a lower specific thrust because of the quadratic dependence on the current. Now the iron losses in turn for both the back iron and the teeth are decreasing because of the quadratic dependency on the electrical frequency. And lastly, of course, the mechanical losses are decreasing because we're going to lower speed as we go to lower specific thrust. Now the internals of the gas turbine core are obviously not at all empty. They're really filled with disks, frames, subsystems. Therefore, it might actually not be possible to accommodate the electric machine within the turbo machineries up to exactly the hub radius. So we additionally applied some factors on the hub radius to come up with smaller installation spaces. And from the left to the right, you see a factor of 1, so 100% of the hub radius being available for the machine, 0.8, so 80% of the hub radius being available, and 0.6 or 60% being available for the machine. And we see that some fairly long machines result if we have to reduce the diameter of the electric machine. In terms of the component masses, we also have some interesting results. We see that most of them increase as we go to very low specific thrust values. There are actually 2 exceptions with our assumptions, the low pressure turbine and the intermediate pressure compressor. And due to the absolute value, we focus on the low pressure turbine here. Now we know that for direct drive engines, the low pressure turbine mass typically increases with a reduction of specific thrust. Now we also have to recall that a gear turbofan, this is a geared hybrid. Recalling a gear turbofan, we recall that this suffers less from the underlying implications, and you can see the details in the paper, because the turbine rotates much faster and therefore can keep the number of stages longer across a given range of specific thrust values. So what we're seeing here really is that this weight reduction for the low pressure turbine is really due to us not having to increase the number of stages across this range of parameter values that we're covering with the sweep. terms of the total masses, we see that there can be a minimum at some intermediate specific thrust values, and the values are lowest for the spinner at low pressure turbine installation option and the intermediate pressure compressor at low pressure turbine installation option. Now, with all the assumptions we made and the analysis, the installation inside the intermediate pressure compressor comes out advantageously, with the exception of the integration issues. Now, if we choose to mount the machine inside the spinner, then actually mass might be a decisive factor, less so the efficiency. And concerning the design trade-offs that we identified, we can note that concerning this shaft speed trade-off that is in the title of our contribution here, the gas turbine essentially behaves as we would expect it. As we go to lower shaft speed and specific thrust, it becomes more efficient. Now, the electric machine, it can actually have the opposite trend. We also saw that the reduction in radial space for the electric machine can be quite costly in terms of the length and therefore also the mass of the electric machine. We also saw that the lens type, or more generally the Glen type designs, they actually look fairly advantageous from the instantaneous specific fuel consumption values, but the designs, they use fairly large fans, and the nacelle weight, the drag should really be taken into account. They were not studied here. And these designs, they also become less efficient if we throttle them to the correct cruise levels. Of course, there is also future work. We think that the installation effects and then the nacelle drag should be studied, such that we can use installed specific fuel consumption, or ideally even block fuel, to question and review these results that we're reporting here. And we also think that more detailed component design would be very helpful. For instance, partitioning the electric machine to accommodate the classic compressor discs, or coming up even with an integrated design of the discs and the machine. With this, I'd like to thank you for your attention. I hope that the material presented was interesting to you. Please join us in the live Q&A or reach out by email. Thanks again, stay safe, and wear your masks.